ICP folks in the audience? Awesome. Okay, you get credit for this this one. For those planners that are out there, several of our workshops and sessions did qualify for credit, so this is one. All right, so I want to introduce Stephen Mather as soon as my phone is off. There. Okay. Stephen has been working in GIS planning and related fields since 1998, working for the last 7 years as a GIS manager for Cleveland Metro Parks. He has been interested in the application of the computer vision to geospatial analysis since 2004 and has recently initiated the Open Drone Map project, a project to bring together and extend a suite of open source computer vision software for use with the drone and street level images. He is also co-author of the PostGIS Cookbook. Welcome, Steve.
Oh, it's fine. It's fine. It's supposed to be like that. It's by design. So we'll. Actually, now we're recording the video. Can't change it. That might be a problem, but. It's a lot more interesting when it works. Oh no. There we go. All right. Well, this would have a list of members of the Open Drone Map project. This would have a list of contributors. It's nice, isn't it? I'll read a couple of them. We've been working with a couple groups out of Sweden, Spotscale and Mapillary, and then there have been a bunch of contributors, a handful of contributors on GitHub. By name on the GitHub website, D. Baldwin, Jesse Crocker, Solar 2000, Mikkel Massett, Flosher, Fawcett, Multi-D, Wild Intellect, and Petrosova. So, and these are our data contributors. So we've got Aaron R., Michelle Tobias, Fred Judson from Ohio Department of Transportation, Mercado, and the Gowanus Low Altitude Mapping Project. It'll be interesting to see if any of these slides work. This will be. Oh wow. Okay. So, and this is a project that was forked from Questa or I should say Bundler Tools by Questa. And the basic. This kind of started as a joke. There was sort of a geo hipster call for what are the emerging technologies in 2014. What are those things which are going to transform the cool geotechnologies? And so I joked that it would all be about go from these worldwide satellite maps of everything down to just very finely handcrafted pixels from people flying drones locally. And then I thought, well, that's not a bad idea. I've been thinking about the computer vision space for a while, and what we could do with taking those unreferenced photos that come from either drones or street view level data and turning that into geographic data. So how do we make sure that all this data that's being collected, some of it sort of arbitrarily, some of it for other purposes, how can we change that into geographic data? So with a set of input images, we get from Open Drone Map a point cloud, a digital surface model, a textured digital surface model, and orthophotography under the right conditions with the right inputs. And the basic question of why do this is all of a sudden we go from having from having relatively low resolution imagery. Well, we thought it was pretty cool when we first got it, the 1 foot or the the 6.5 foot imagery, to no presentation at all. I'm going to switch to my laptop.
Yeah, good plan.
Is it, we're not be recording, but,
Yeah, it's all right. Well, it's still recording the audio.
okay, great. All right, sounds good.
Keep the audio going. And
Let's see.
go over here.
Yep.
Okay, this-
I can hear every time I use the microphone. All right. Give me just a moment to configure. About 2.5 years ago, about 5 days before my daughter was born, I did a presentation on another project at Ohio GIS. And it was the only time I've had a complete epic technology fail. Nothing worked, not other people's laptops, the network didn't work, and it was interesting. But because my daughter was due at any moment, I was so calm. I gave a 30-minute presentation on it, no slides, and I apologize, I don't have a child due any moment. This won't be quite that level of relaxed, but let's see what we can do here. Okay. Yeah, there we go. Maybe.
You didn't save it. You said it.
Let's get everyone's user in the audience. Okay, there we go. Dr. Knoll. So here are the members that have shown up on GitHub. Actually, I did slides from a couple days ago, so maybe a couple that I missed. Contributors, which I read off. Contributors to the data portion of it. So in addition to OpenDroneNet itself, we have a repository of test data. It's been a blessing and a curse because test data shows the problems with the project as much as the things that work. So that's been fun.
Drag the presentation over there.
For the record, I'm no longer calm. There we go. All right. Okay, and the project was forked from another, so it's been interesting fielding questions. So what does it do? Basically, the basic premise is that you take input images from a small UAS or from street level, and you can generate that point cloud digital surface model, texture digital surface model, orthophotography. And what this enables us to do is go from this relatively pixelated view of the world to be able to generate orthophotos, since color infrared. Generate orthophotos of much higher resolution. What kind of resolution? Well, typically be an inch, 2-inch pixel. So you're looking at somewhere between 10 and 50 times what you see from most fixed-wing planes at this time. But there's a problem here, right? If you've got a fixed-wing plane with a highly specialized sensor with really nice lenses, well understood geometries, flying at 400 or more feet, you've got a nice constrained problem space. You got onboard GPS, great GPS. You've got navigational controls. You've got you know where that plane is within, pretty precisely at any given point in time. Post-processing on those images is actually relatively simple. The problem is when you've got a less constrained system, you've got commodity cameras, you've got a random set of images, the problem space becomes a lot more complicated. So, borrow some slides from Kavita Bala's Cornell course here on stereo versus multi-stereo. Actually, really, it's about multi-stereo. So the stereo case is there on the left. That's not. I don't think that's a ortho imagery. But stereo images that well referenced. We know the separation of the images. We know all sorts of things about it. Versus multi-stereo, where you've got all sorts of cameras you don't know ahead of time, maybe what kind of optics you have associated with them, but you want to use the information that you can match between them to reconstruct something. And the basic problem space is if you have 3 cameras of taking an image of the same object, then you can identify points in each of those cameras that correspond with the same places in the real world. And assuming you've corrected for your optics and some other stuff, so you do some nice little math that traces between, in 3-dimensional space, traces the intersection of those 3 points back to their origin. You do this over the whole image, and you can reconstruct in relative space where that object is relative to those 3 cameras, or where those 3 cameras are relative to the object. Each of those points that you identify then becomes a portion of a point cloud. So there's a few steps to getting there, right? So we need to do feature extraction to figure out what our features are in the first place, and then we do able to match those features. We can have relatively complicated scenes from a variety of different cameras. So we need to identify features that are in variant transformations. Those transformations can be changes in brightness, so different brightnesses in the different images, different levels of contrast, and also rotation, translation, scaling, etc. And then we feed it all into some fancy nonlinear least squares math. Within the use case for small UAS, we've got this small UAS flying above the ground. This is just topo lines over a hillshade. Small UAS is in black. The viewing footprint of the small UAS is there in purple. We fly that over. We want to get at least 3 views of each given portion on the ground, which means we want 80% overlap roughly in our image set. Boom. Now we've got all those little individual footprints all overlapping, a bunch of little pictures from each place where that drone flew. Now we can construct a point cloud from those data. That's pretty cool. Now, it has some limitations. So LiDAR has the ability, you incorrectly say LiDAR has the ability to penetrate. LiDAR has the ability to see through the gaps. This does not have the ability to see through the gaps here. It does not work well with vegetation unless you want the top of vegetation, unless you want the top of that vegetation model. But, that aside, we create a surface model from that, so we basically turn that into a mesh. And then we can paint that mesh with the original photos. If we do it really well, we do some smoothing in between, et cetera, et cetera. That's some stuff forthcoming with OpenDroneMap. And then this is a mesh of a farm scene in Poland from one of our contributors. And this, we can then take that, once we have external information about where the z-axis is, and we can turn that into a formal orthophoto. You'll notice in this case, we don't have ideal coverage. This was actually kite flight rather than a drone flight. So if you look closely, you'll see some gaps where we don't have any texturing. So you may be asking, oh, well, that's kind of cool. Where do I begin? How do I do it? So we've got a website, opendronemap.org. It's actually hosted at opendronemap.github.io/ODM. And there's a repo for the data and for the actual code. There's a wiki that's cut off there. So where there's the beginning of the W, that's wiki. There's a wiki, and that's evolving, but that's community driven, and it's being updated and written pretty quickly. And there's a couple YouTube videos on how to install and use this. A couple caveats. It is Ubuntu only, so if you're running on a Windows or a PC, Windows or Mac, there's a separate repository that allows you to run it as a Vagrant instance, so you can still run it and use it. It is a command line tool at this point. There's, I think, there's at least 3 different projects that I know of working on putting this as a backend on a web server, so you can just upload a set of images and get back your data. We're working on that at Cleveland Metro Parks, and we'll release that as a project, and these 2 other folks are working on it, including the state of Ohio is likely to start working on that within the next 6 months. But if you're a Linux user, or you're comfortable with just sort of typing out commands that you don't really know what they do, it's not that hard. You run these 4 commands, and on Ubuntu, you have everything you need to go. And then you navigate to your directory where you have all your images, and you run the run script, which is, for irony's sake, it's in Perl. And then you wait. If you run this on your laptop, you will wait a while. If you run this on a larger machine, like maybe an Amazon instance, DigitalOcean instance, or an actual workstation, it's probably in the range of a couple hours, 2 to 3 hours on maybe a 32 gigs of RAM, both processors. And then all the results go into a results directory. That results directory, the name's going to vary depending on what parameters you use. You can choose to use parameters or not. If you use no parameters when you run it, it'll be in an output directory called reconstruction with image size 2400-results. And this is where we go from the presentation didn't work for the first 10 minutes to I'm going to do a live demo. Just a moment. Because those always work. So I'm not actually going to demonstrate running the command, does anybody want to sit around for a couple hours? Okay. So we won't run the command. But once you get the output, then you can use MeshLab, which is readily available on all sorts of different platforms, and you can actually open the mesh. So go to File, Import Mesh, and you'll see my wonderful organization. Within, let's go to a directory that is structured how you would see it. So this is the GLAM data set from New York, from Public Lab. Inside this is reconstruction with image size 3000, because I used a parameter, I set my image size to 3000. And inside a subdirectory, there is the textured model. And there's our textured model. Now, the better the data that goes in, the better the model that comes out. So this is actually from a Bloom data set with someone walking down the street with a Bloom. So there's some limitations as far as what kind of coverage you get with that. But still, it's a pretty nice result. Let's see. Go to Langley. This is a very nice result. This was a very nice product from this was actually the phone with the drone by Aaron Rasico in Langley. Ooh, that's interesting. Hold on a second. So Aaron flew the city street, and he got very nice results for the street itself. The flight itself was largely through the center of this corridor, so as you get to the edges, you get some weird results, but pretty snazzy stuff. He had, I should say, so I mentioned that this does orthophotos. This does orthophotos under 2 conditions. If you've got an onboard GPS in your drone or your balloon or your kite, that is feeding that information into your photos. Or if you create a ground control file and include that when you run it. So if you include that ground control file, then you basically specify this corner right here is at XY in this photo, and et cetera, until you've got at least a minimum of, I think it's a minimum of 3, I would recommend 4 or 5 ground control points to reference that. And then by default, it'll actually create an ortho photo for you. Look at another model here. Oh, let's see. So I'm going to show you a bad result. because depending on what you do as far as data collection, you can get some very, very interesting models. There we go. So this might not be what you expected when you collected your data. This is why we have test data sets that challenge the assumptions of the inputs. If we look a little closer, we'll see that inside here is a sidewalk coming out of the tunnel. It actually is out of the tunnel, but we're not actually, the tunnel's behind us here. Coming out of the tunnel. And this is one of those cases where there's not enough information. And so where you've got enough information, which is this, this 8 feet of sidewalk, it's actually a pretty decent model, a little bit of noise, but it's a pretty decent model of that sidewalk. But outside that area, there's not enough information as an input. All right, and I'll show you one more. Oh, I'll show you 2 more. I really like this one. So if you've got good input, so how do you specify good input? 80% overlap, maybe aim for 90%. If you've got onboard high resolution video, that's a great way to do it. If you've got a $30,000 drone, well, okay, you can just program it to do it. Maybe a $10,000 drone. But if you're doing this recreationally, get some high resolution video, and you'll be in pretty good shape. This is a flight. This is from a flight also by Aaron Racico. Let's see, and others. And this is over some sort of. Actually, I don't know what this facility is. I just know that it's got some odor associated with it based on the name. So they flew this facility, the full model. It's actually really interesting. There we go. And the other thing that's nice to do, although it's not absolutely necessary, but if you want to make sure that you don't have too much bias in your model, moving both through X and Y and through Z is important. So if you're programming a flight with a drone, fly 2 heights, have it fly 2 heights, have it fly twice, or fly 2 heights, and then make sure you have plenty of overlap. If you're doing a balloon, chances are you're going to be up and down anyway. You're going to get that vertical pretty easily. You're going to struggle a bit with getting the horizontal. Now, if we really sort of interrogate this model, we'll see that it doesn't know what's going on underneath, and so this is an input issue. There's some other issues that long term, I don't think there's no software that I know of that deals with well, and that is edges. So one of the things that's sort of on the long term plan for OpenDroneMap is to be able to input 3-dimensional break lines so you get actual proper photometric outputs and better modeling of the overall shape of things. We'll do one more. This is that Poland, that model from Poland. And this was a kite flight over a farm. So this works really well over where they're flying. So the buildings are pretty well referenced. But once you get outside that, Howard operating the 3D on this so you guys don't get nauseous, but once you get outside that, then you get to the edges of where the model space works well. So I'll pause there for a moment, I'll take questions, and then I've got just a couple of things. Yeah?
You said this takes a couple hours to process. Are you using any sort of video acceleration?
Not yet. So Visual SFM, which will generate a point cloud in the original camera positions, actually uses GPU acceleration for matching. That's something that we want to integrate with the project. Visual SFM itself, I believe, has a non-commercial. It can only be used for non-commercial use. But the software behind that, the SIF GPU software behind that, we could and probably will integrate into this. The other optimization that would be ideal to include if you have information about the original camera positions, then you only match between ones that you expect to match, so that you don't have that you don't have an exponential curve to the difficulty of the problem as you add more images. Yeah. Right. So and there's some issues with that because I think if you've got a commodity drone, you may not have good information about. You may think you have good information about orientation, but you may not. If you've ever taken your cell phone, which and had something which takes advantage of orientation and like shaking it, you'll know that suddenly the phone gets very confused as to what way it's oriented. But if the GPS is good enough, that's at least a starting place for doing those optimizations, and that's a relatively easy problem to solve. Oh, well, RTK you can just fine.
And second of all, do you have any integration with PostGIS backend?
No, not at this time. It's built on bundler tools, PMVS, CMVS, and all of those write really cryptic text files that I know there are people who understand them well. I know a few of them. It would be good long term to write persistent to something else. Yeah. Oh, I should say I didn't repeat it back his questions, but he asked whether it writes to PostGIS backend as far as the ephemerals. Yeah.
When you generate these textures, what can you do with them after you get the painted textures? Can you put them in anything besides MATLAB?
I don't know. Do you have anything we can put it in?
Not for the 3D textures, but PostGIS has the ability to do 3D surfaces, right?
Yeah. But I don't think it'll do textured surfaces. So, yeah, it's interesting because it's the question is where should you be putting the data long term, and I suspect I know Paul's thoughts on putting textured meshes into PostGIS, which is what? Wait, exactly why? But you can store where the texture mesh is in the database, and that would be a useful thing to serve it up. So, cool. So, let's see if there's anything. Yes, so let me show you what the contents. The question was, can you tile them and cache them? One of the things so initially we thought we were going to use MeshLab to do the texturing, but MeshLab actually doesn't do well. There's some issues with the size of meshes that we're talking about and the sizes of textures that we're talking about. Sitting here. At the same time. They don't go together for me. So if we look at one of these meshes, it actually is already tiled. So we've got several different levels. And honestly, the structure of this, I can't say I fully understand. But yeah, there's some structure there. And that's why, in spite of being relatively large meshes and being these are full resolution textures. So this is the actual resolution of the original images. When I loaded MeshLab on this little laptop, it does just fine. It's I don't know the name of it. But I'll get back to you on that. I'll give you my card. So, places where you can get some information on this, opendronemap.org or the actual canonical location, which is on opendronemap.github.io/ODM, and the various links there. And I've got a question for you guys. Can anyone tell me why the Dr. No theme, the Dr. Null theme? Any guesses? Other than spies and drones in the air. So is anyone familiar with Null Island?
Raise your hand if you're familiar with Mill Island. Yeah, so, you know, the big problem of all this drone information being collected is it has no, by default, I mean, there are 6 main sort of commercial packages for post-processing images to geographic data. None of them are particularly affordable. One of them is relatively affordable, but only for institutional budgets. You got all these images. You got no geography associated with them. They all go to Mill Island. They all go to 00. There's no reference to that data without a software stack that allows you to do that. So I was going to wear like a white turtleneck and decided that you know, one too many things. Thank you.
Do we have any additional questions for our speakers, either speaker? No? Okay. Well, the next thing is lunch. So